And here we go. All right, so electric field distance is 11.9. I'm doing right now 11.9. Here we go. So as here, it says electric field distance x from a point be written as E equals 4x squared. What's the voltage between the point 4 to 1? Last time we came with a formula that the voltage is the what?
The integral.
Integral of the electric field with respect to distance. Agreed?
Yeah.
Okay. This is huge. This is, you're going to use this about 8 times on the AP test, and you're only going to have a total of, category free response questions is 1 question. You only have 38 questions. Use it 8 times, roughly.
Okay.
They have microphones. They probably say, "Oh, let's remove that one, put this one." I said it's like 7 times. Okay. So, so in this case, the electric field is given to you as a formula. So it's going to be written as 4x. Is that a -2? -2 dx. And we're going from 1 to 4. So I'm going to go V equals. So I raise this power by 1. Divide by the power I get, so I get a negative from 1 to 4. Great. So the voltage is therefore -4 over x from 1 to 4. So that becomes -4 over 4 minus -4 over 1, which gives you a positive 3 volts. Agreed? Great. That's how you do problem number 1. I know that's not what you asked for, but does that make sense? Okay, so we're going to roll forward from there. Another thing we could end up doing is we could look at this, say electric field 4 meters from a positive 1.33 times 10 to the -9 Coulomb charge. So how do I find the electric field from a point charge? Who wants this one? Everybody should be like, me. This is an easy one. Yes, sir.
E equals KQ1 over D squared.
KQ1 over D squared. So K is 9 times 10 to the 9th. The Q I gave you is 1.33 times 10 to the -9th, all over 4 meters squared. And what do I get for the electric field at that point? Waiting. Peter's got it.
Wait, what was that? 0.731.
0.731 newtons per coulomb sort of electric field, right? Or volts per meter. Agreed? Make sense, everybody? We got that. This is one this formula that should be in your bag of tricks, even though it's not on the formula sheet anywhere. Has to be there. You can derive it from the other ones, but why do that? You should have it. So far, so good? Happy trails. Moving on to 3. That was 3? No. Yes, 3. Now I want a distance x from that same positive charge. Peter, tell me what would be a distance x from that positive charge?
4. It's just 4.
It's KQ over D squared, right? From the point charge?
Yeah.
Right? We don't know what the distance is. Now I'm saying let's make it a variable. Okay? So how do I do that? 9 times 10 to the 9th. What's my charge? 1.33 times 10 to the -9th. Is that right?
Yeah.
Divided by the distance between them, which is x squared. So that would be my electric field, a distance x from it.
That's easy.
So just
Agreed? All right.
Can you leave it like that, or should you multiply the top?
I would draw the top. Top is 4, right? So this becomes 4x to the -2. It hits back to the very first. I think it's 4, isn't it? Somebody check me. Worksheet's still rough. It's fairly new. Has problems probably. Good?
yeah.
Okay, so I want to know a voltage for a place 4 meters from the positive test charge. Now, voltage, please listen to me. This is Mr. Resnick's terrible thing he's doing to you. So listen, that should be potential difference, right? Voltage is going to be potential difference. Potential difference implies a voltage spot from one spot to another spot. I only gave you one spot. What is the other spot?
Oh, didn't you say what is, you told us to change it.
Did I actually change it?
From
Yeah, you
1
said what
meter.
is the potential difference from 1 meter to 4 meters?
Oh, that's even better. So from 1 meter to 4 meters. So we're going to go ahead and get that. Good. I fixed that. So potential difference, so between 4 and 1 meter. So how am I going to find the potential difference?
Integral.
I'm going to integrate this thing, right? I'm going to take, what's the voltage? The voltage is equal to the integral of the electric field dx. Agreed?
So it's actually 12x to the -2.
Yeah.
Which is going to be 4x to the -2. Wait, am I doing wrong? I'm just writing the formula down.
When you multiply the tops
not
up
4.
there, you
Oh.
get 12.
I get 12?
Yeah.
I'm glad you checked me. I'm going to back up a step here. Is everybody with me? Because I don't want to make more trouble than I have. It's 12. We're okay? Everybody 12? Good? Okay, so I'm going to plug in 12x to the -2. dx from where to where?
1 to 4.
From 1 to 4. It says from 1 to 4, so go 1 to 4. Whatever I change it to. Good? So I do the raise the power by 1, divide by the power I get. From 1 to 4. So the voltage is going to be -12 over 4 minus -12 over 1. And I'm getting, what do I get? 9 volts. Now I'm ripping. Is everybody okay with me? Sharp bunch. Now, 5 is what you asked for. And finally got to 5.
Yes.
I apologize for taking so long to get to 5, but we're at 5 now, right?
Okay.
Okay. So 5, the question is, what is the energy necessary to move a 4 coulomb charge from 1 meter away to 4 meter away? Now, there's 2 ways to approach this. Are we ready? What are the 2 ways to approach this? First way, why do we care about what does voltage do for us?
I don't know.
It takes everything out of the system and just gives me energy per unit charge. Whatever's in the system is taken care of. It's energy per unit charge, right? So if I just take my voltage times my charge and know the potential difference, I solved for it. My potential difference was 9 volts between those 2 points, right?
Yeah.
So I take my voltage times charge, I get how much energy it takes to move from one to the other.
Okay.
Do I not?
Yes.
And so then I'm just going to go U equals 9 times the charge I'm delivering is it 4? 4. And I get 36 joules and I'm done.
Wow, that was, wow.
It's super easy if you do the problem before it correctly and you know what VQ is, which is the first question you asked, and so that's the same idea. Okay, so we established voltage, so I can just go, now I'm going to put 2 coulombs, I'm going to put 8 coulombs across, now I'm going to put 15 coulombs across. Once we got the voltage, we can just do whatever, right?
Okay.
We just, how much charge am I delivering, times the voltage, how much energy I have for doing that. Or if I let go of it, it comes sliding back the other way, it's how much energy it loses, which is how much it gets for kinetic energy, whatever else I want to play with.
Okay.
Good so far?
Yeah.
All right, so that's said. Now, that's one way to do it. Go through electric field to voltage to VQ equals energy, right?
Uh-huh.
So I can do that. What's the other way to do it?
The negative K Q1 Q2 over R.
Right. So we know the potential energy formula for something is going to be negative KQ1 Q2 over R. Agreed?
Yeah.
So I'm going to go ahead and use the potential energy formula on the 2 things. So in this case, if this is 9 times 10 to the negative 9th. The first charge would be 1.33 times 10 to the negative 9th. Is that right? No. What did I do here? No, this is, whoa. Holy monkeys. Starting over again.
Same answer though.
9 times 10 to the 9th, negative out in front. And then this becomes, we should get the same answer, right?
Yeah, that's.
Do we
I've
not?
done it twice and you don't get the same answer.
Brad.
So,
Negative 9th. What's the charge I'm delivering?
4.
4. And I'm starting at 1. And then I'm going to minus, going to 4.
Oh, okay. Maybe that's why.
Can't you just do 3 on the bottom?
No. Would that give you the same
That's
answer?
what I did. No, it didn't.
Just don't write.
Would that give you the same answer?
No.
Because electric field is changing everywhere, it's not linear.
Yeah.
1 is different than 4. And everywhere in between is sloped, right? So I can't just put in a 3.
Wait,
Lost my
you
train
do
of
the
thought.
1 over the 4.
Times
1
4
subtract
over 4.
minus the 4.
Over 4, right? right? It's difference, right? It's the difference in potential energy. Should be how much energy it takes to deliver it. And what do I get? Please tell me 36 joules. Somebody's got to do it and give me 36 joules, and I'll feel better about life. And I can retire in the countryside, take care of horses.
Yeah, it's 36.
And my stinking roof that nearly blew off. It's 36 joules.
Negative 36.
Wait.
But it's
Is it negative?
Negative.
Right.
That's what it gives us because you.
Now, I told you about signs until I'm blue in the face, right?
Yeah.
Are these both positive?
Yeah.
So delivering from 1 to 4 does what to my joules?
It makes you decrease it. Wait,
That would be losing energy, wouldn't it?
You push up your peak. Yeah.
Losing potential energy, right? Because they're both positive. If I move them apart from each other, I'm losing energy.
Wait, what?
If they're both positive.
If I've got a positive here and a positive here, what do they want to do?
Go
There
away
you go.
from each other.
Move away. So if I let go of it and make it go from 1 to 4, I'm going to lose potential energy.
Yep.
Which, by the way, isn't lost energy. Where's it going?
It's gone.
Likely kinetic energy, right? Or sound or heat or something.
What if you're like holding it there?
Yeah, if you're holding it there, then you got no energy. You're not getting any energy out of the system.
I don't
Okay.
understand.
If it moves from here to here, it's got to dump 36 joules of energy. You could pick how it dumps that. Is it going to be moving at the end? Is it going to make the laughing Kathy doll laugh? What is it doing? Yes, ma'am.
I don't understand how you figured out which way it was going.
Which way is what was going?
Or like if you're gaining or losing the
Okay.
potential energy.
Here's what we were trying to discuss right here. I've got a positive charge. This one's fixed, right? Sitting in the box, can't move. With me?
Uh-huh.
I take this charge from 1 to 4.
Yes.
It's a positive charge, right?
Yes.
So if it's a positive charge, I move from here to here. What's going to happen? Is it going uphill or downhill? Which way does it normally want to move?
Away.
Away. So if I just let go of it, it's going to roll down this hill.
Yeah.
So I'm going to lose energy. The system is going to lose energy,
Okay.
right? Now, again, that energy has to go somewhere. So it's either going to be moving really fast here, or it's going to be make the lift. It's going to make some sound and heat getting here. It's got to dump energy to get to here.
Okay.
Right? If I move it the other way, I'd have to do 36 joules worth of energy. Because it's gaining 36 joules worth of potential energy.
Okay.
This is the thing we're talking about, where signs on electrical fields is really, really difficult, and on voltage is really, really difficult. You have to look at the problem and figure out from the context of the problem.
Okay.
Okay, and I need to pass out. Let me pass out that formula sheet. So it says the formula says E equals negative dV/r, right?
Yeah.
And I said, well, obviously this is the same formula that we're playing with, just written really oddly, right? With a negative sign, which we did not talk about. Why is that a negative?
Because
We got a positive voltage here, did we not?
Yeah.
What should we have gotten?
a negative voltage.
If I use this formula with a negative in front, I would get a negative voltage.
Well, then won't you always get a negative voltage?
No, because if this gave you a negative inside, I'd get a positive voltage, right? If my signs are different on these, Kara's with me?
Mm-hmm.
If my sign here is negative,
Uh-huh.
then this would give me a negative. So negative here, so it would give me a positive when I got done, right? This would be negative, and so then as I travel through, I'd have negative here, and then when I switched it out, this would become positive, and then the negative part would make it negative again. So that's where that's why those didn't match. Do you understand me?
Yeah.
Now, my personal advice is this. Think about the situation. And remember, you were already talking about positive test charge. So what we should have done at the end of this problem, and I knew I was coming back to this anyways, but for this point right here. When I have a positive test charge, and I have a positive charge, and I'm moving it that way, my voltage should be negative. I'm losing energy per unit charge. Okay, so I should have that built in. Okay, and so my personal opinion is you can forget about the negative because it's going to haunt you anyways. But try it. I mean, worst case, you get the right answer, and if you don't know how to fix it, you just leave it. Right? Make sense? But always look at your answer, because it's amazing how often, even if you do the math exactly right, there's some little trick in there that's messing it up. Okay, so if I get a positive moving from a positive, it should be downhill. It should be negative voltage. It should be negative energy.
Okay.
When I get done. Okay.
Yeah.
If it doesn't give you that, 99 times out of 100, just switch the dang sign. You did the math right. You just got a glitchy negative in the wrong place. It's going to the left, and so you got double negative, and somehow that didn't work out for you.
Okay.
Something like that, okay? So again, emphasis on that.